All right, this is the last part of the term 3 review. This one says to find the derivative. We're using a quotient rule here. Quotient rule says to take the bottom, so e to the 6x, times the derivative of the top, which would be 21x squared, minus top, times derivative of the bottom. Derivative of the e to the 6x is e to the 6x, repeated, times the derivative of the exponent, which is 6. Okay, all over e to the 6x squared. All right, so now if we kind of try to work our way through it, we see we have 21x squared e to the 6x on the top, and that matches up with A and with B. We see that we have, if we put this together, 42x to the third e to the 6x there. All right, that 42x to the third e to the 6x, that kind of works there and there, okay? But now the question is, well, what goes on the bottom? And you'd be very tempted to square 6x, get 36x squared, and think A is your choice. Everything else is matching up perfectly with A. The problem is that's not what this squared is, okay? B is tempting too, but they didn't square the bottom, right? And so here's the deal. They have taken that e to the 6x squared. That would be e to the 6x times e to the 6x, which should give us e to the 12x. And that's not one of our choices. So a little frustrating there, right? Well, here's the deal. It's actually a simple fix. What they did was they took this e to the 6x that was in both of these, and they pulled that out. They have e to the 6x times 21x squared minus 42x to the third over e to the 12x. And then they said if this canceled here, these 12x's subtract 6x would give us 6x left over. So while it looked wrong initially, well, it is wrong here, it ends up being correct once you do the canceling. C is our choice. So if you did all this beautiful work and you have this set up, you know the quotient rule, you know how to take these derivatives, you did okay there. This is a very sneaky extra step that I would doubt they would ask you to do very often. Okay. Find the equation of a tangent line. They already gave us a point, so we need a derivative. Derivative would be 1/2 2x plus 4 to the negative 1/2 times the derivative of this, which is 2. So the 2 and the half can go away right away. So our derivative would be just this to the negative 1/2, which I'm going to rewrite as this. It's down on the bottom because of the negative. It's square root because of the half. And now if we put 6 in there, we're going to get 1 over the square root of 12 plus 4, which is 16. And this gives us 1/4. That's our slope. And so therefore it's got to be one of these. And if I were to create this equation and then distribute and try it from there, we're going to get D as our choice. All right, then we go into here. It says water's dripping into a vase at a variable rate in terms of cubic centimeters per minute. And every 2 minutes we find out what that rate is. So can we use a right-hand Riemann sum with 3 equal subintervals to find the approximate rate at which the water drips into the vase over 12 minutes? Now there's 2 things you got to be real careful of. First, they're asking us to find the average rate, which means that we're really trying to find 1 over 12 times the integral from 0 to 12 of r of t. So it's not just a right-hand Riemann sum, it's a right-hand Riemann sum divided by 12 to get an average. So you got to be careful with that. It's also 3 equal subintervals. So we're not just going 6 of these, we're going from 0 to 4, from 4 to 8, from 8 to 12. Okay? So if I kind of understand that, then I can say no problem. From 0 to 4 to 8 to 12, I'm using the right-hand side to determine the height of it. So at 4, the height was 10. So that gives me 40 in there. That would be my volume from 0 to 4 approximately. From 4 to 8, we're letting the 12 be the guide. Okay, so 12 times 4, that'd be 48. And then for the last one, I'm using 8 as the guide. So 8 times 4, that's 32. All right, so add this up, 40 plus 48 plus 32, that's equal to 120. And we're going to divide that by 12. And so our average is 10 cubic centimeters per minute, which is A. Right. So So again, you want to be real careful. You could easily do this correctly and then get to 120 and not be sure, or maybe divide by 3 and pick D. There's a lot of little things that could go wrong there. All right. Now 12 says, can you use a midpoint Rheon sum to approximate the total amount of water that has dripped over the 12 minutes? And now we're not talking about an average anymore. We just want the actual total. We want just this right here. So we're actually going to do the midpoint sum and then let that be the answer. So from 0 to 4 again, from 4 to 8, from 8 to 12. But this time I'm going to let the midpoint dictate. So at 2, the height was 18. 18 times 4 is 72. At 6, the height was 15. 15 times 4 is 60. At 10, the height was 16. 16 times 4 is 64. If I add this all up, 12, 19, 196 cubic centimeters is our approximation of what fell in there. All right, then we were given this question: air is being pumped into a balloon at a rate of R of T. So that's the water, that's air coming in. There's a small hole and it's leaving L of T. That's going out. So this is in and this is out. Which of the following is true from 0 to 10? Okay, so this one takes the integral of in minus out. Okay, integral of in minus out represents the volume of the balloon after the first 10 minutes. So it doesn't ever say that the volume was 0 to start with. So this is the change in volume. Okay, so if they had said change in volume, I'd feel a little bit better about it, but this definitely does represent volume. I just don't know how much was there to begin with. All right, so I may come back to that if I don't like these other ones, but I would have felt a little better if it had said change in volume. Let's look at this one. So this does 1/10 times this. That's an average. It says represents the increase in volume each minute during the first 10 minutes. Well, that doesn't make much sense. This is an average value type look, right? So this would be the average rate that the volume was changing, not this. So I can get rid of that. Here's another one, represents the increase in volume during the first 10 minutes. Okay, that's what I was looking for from part A, right? So if I had known what the initial volume was, and if they had added that in, I would like A, but now I like C a whole lot better. Okay. Now this says R of 0 minus L of 0 equals 1. I have no idea where that even comes from. Like this is the rate that it was going in minus the rate that it's leaving at time 0. We have no idea what any of those things are. That makes no sense. This is the change in the rate minus change. Again, I have no idea how we would get any of these values. We weren't given even an equation to work with. So the best answer is C. Right? This represents the increase in volume. And then lastly here it says a particle moves along the x-axis so that this is its velocity. At what time is acceleration at its minimum? So if you think about, a velocity graph here, and we want to know when acceleration is a minimum. So it's going to take a little bit of thinking. If I'm looking at my acceleration and I want to know when am I at a minimum, what I'd like to do is then take the acceleration equation, take its derivative, and see when that derivative is 0. Where do I have a critical point on the acceleration? So I'm going to take this velocity graph or equation, take the derivative, which is negative 3t squared plus 9t cubed, okay? And I'm actually going to take the derivative of that, which is negative 6t plus 27t squared, okay? And I'm going to set that equal to 0, all right? And we're going to pull a t out of negative c plus 6 plus 27t left over. And so that's at t equals 0 and at t equals 6/27, okay? So we've done this work, and that 6/27 is the same as 2/9. So I want to make sure that I don't, because I see 2/9 as I see 0 as a possibility, right? So, so this is saying for t greater than or equal to 0. So this is a possibility here. Let's see what's going on, okay? So we've got 0, we've got 2/9 here. All right, now, I need to pick something. I don't need to worry about before 0 because this wasn't true for anything before 0, right? I want to see what's going on before 2/9. Now 2/9 is like 0.2 repeating, so I could pick like 0.1 and I could put that into the acceleration, the derivative here, and see what happens. So if I put 0.1 in, I get -6 times 0.1, which is -0.6, plus 27 times 0.1 squared, that's a 0.27. I end up with a negative value there, okay, which means my acceleration is decreasing from 0 to 2/9. And then if I pick something bigger than 2/9, just pick 1, put it in, I get -6 plus 27, I get a positive value, which means my acceleration is increasing. So starting at 0, acceleration goes down until 2/9, and then it increases past that. So when are we at our minimum? At 2/9.